This is a short video aiming at providing an overview of the different ways motion can be applied in the AnyBody modeling system. There exist similar overview presentations on how to apply forces and reading out forces, and also presentations on the AnyBody managed model repository. First, an introduction slide on the AnyBody modeling system. AnyBody is basically a multi-body dynamic system. It's developed in-house for musculoskeletal analysis. It's a fully self-contained system. There are interfaces to motion capture, CAD software, image-based bone and muscle data, find element software, and office systems. It has an open body model, and it's broad and deep model, and there's a broad and deep model validation, and there is an API for embedded use. So AnyBody is a multi-body system based on what is called inverse dynamics. AnyBody calculates the forces associated with the motion and the system. So we are looking for the internal forces in the body, which are hard to measure or calculate. This means that the flow of logic is that the system takes the body model consisting of the bones, muscle, ligaments, and joints as input. The movement is also the input, or the event there is no movement, then the posture is the input. Additionally, also the loading on the model, the boundary conditions is the input. The output is then essentially the internal mechanical properties of the body, so forces in the individual muscles and joints, muscle activations, mechanical power, and muscle power, and these kind of properties. What we will be dealing with in this video is how to apply the motion to the system. We control the motion or kinematics by adding constraints. Constraints is being added to a kinematic measure, and a kinematic measure is something which measures kinematics somewhere in the model. These measures comes in different flavors. There are translational measures in 3D, there are rotational measures in 3D, there is a center of mass measure, there is polylines where you can measure distances along between points. There is a point surface measure, and you can also do combinations of the above mentioned measures. So these constraints can be joint constraints. So for example, a revolute joint which constrains 5 degrees of freedom, 3 positions and 2 rotations. It can also be a constraint in form of a driver, which can be a function of time. So you can specify that a point on the body should follow a recorded marker, for example, or an elbow angle should move with a constant speed. So these kind of constraints are all based on kinematic measures. Additionally, the constraints can be both hard and soft. A hard constraint needs to be fulfilled within the kinematic tolerance. So this would be, for example, the joint constraints in a hip joint. A soft constraint is something which the kinematic solver will try its best to minimize, but it will allow there to be an error above the kinematic tolerance. An example of that would be a marker. There are different for this reason there are different types of kinematic solvers. The default kinematic solver will solve the hard constraints only, and the system needs to be kinematically determinate. So there needs to be as many constraints in the model in terms of drivers and joints so that it matches the number of rigid body degrees of freedom in the model. Then there is the redundant kinematic analysis, which allows the soft and hard constraints to be mixed, so it solves the hard constraints and compromises on the soft constraints. This solver is used, for example, for tracking motion capture data. And finally, there is an option for kinematic optimization, which allows the constants in the model to be optimized. This is used, for example, when you want the model to automatically scale to a point cloud of markers, so you can make the model size fit to the recorded point cloud of markers automatically. We have categorized the ways that the motion can be added into the model in these 4 categories. So we have measured motion, we have environment-driven motion, we have voluntary motion, we have force-dependent motion. We will now try to go through the different categories, showing some examples on ways that this can be done, but keep in mind that it can all be combined. First, it's standard motion capture data. So this kind of data comes into the model in terms of as a 3D file. So this model has a redundant marker configuration. So there are soft constraints which makes compromises on the marker location, and there is also an automatic scaling from the data that allows the human to be scaled according to the cloud of markers. Additionally, it can also optimize the location of the markers. In the model repository, there are streamlined models which has been designed to ease the process of driving a model with motion capture data. There are 2 kinds of models. The AnyGate model is a model designed to make it easy as possible to drive the model. This model requires a certain marker protocol to be used. It's the plug-in gate marker protocol, and it requires also a static trial to be present. In the application folder, there is also a model called mocap model, which is a more flexible model which can easily be adjusted to different marker protocols. Another way of getting recorded motion into the AnyBody modeling system is through the BVH format, which is essentially a stick figure driven by joint angles. The BVH data may come from XSense, Kinect, NMSU, or similar systems. The data is being read into AnyBody using an AnyInput BVH object which creates and drives the stick figure. Then what is left is to hook up the human model with the stick figure. The video example displays such a model driven by a motion recorded with XSense from a snowboard rider. Using this concept, it's also possible to scale the human model automatically to fit the size of the stick figure. Another way to drive the motion is to drive it through the connection to the environment. The system handles at the same time both the human and the environment, and it handles both open and closed kinematic chains. In this example, which is a leg press machine, we drive the motion of the weight, and by attaching the feet to the plate, the motion of the knees are described. This is another example of an environment-driven model. Here, the center of mass of the entire body is used to drive the body to be above the feet, and there are constraints between the hands and the feet and the machine. So these constraints together describes the kinematics of the model. This model has been read into the AnyBody modeling system by using the CAD interface from SolidWorks. So it's a machine has been created in SolidWorks and then exported directly to AnyScript via our SolidWorks to AnyScript translator. Voluntary motion. So this category of motion we have called voluntary motion, and here we mix the hard and soft constraints. So in the model, in this video, you see we drive the position of the pelvis to be fixed in space, and then there are soft drivers for all the joints in the model, to all the joints in the model, which drive these joints to which tries to drive these joints to a neutral position. At the same time, we have the hard constraints between the hand and a coordinate system, which you can see being moved around through the GUI. So the model tries to compromise between the soft drivers on all the human joints and these hard constraints between the pelvis and the hand to be able to meet the hard constraint. It compromises on the soft constraints. And this is an easy way sort of to control the motion to control the motion to obtain different postures. The last category of motions are the force-dependent motions. So what we're looking at here is small displacement or motions such as internal joint displacement, which cannot be measured or guessed upon with the synthetic approach. So for this type of problems, we need the force-dependent kinematics, which lets the user calculate the small motions in the joints, which are then determined as a consequence of the force equilibrium between the muscles, the ligaments, and the surface-surface contact. So here you see two examples of this. There is a knee motion example, and there is a spine flexion. So in both cases, the overall motion of the model was given in terms of a flexion of the joint, and the model then calculates the remaining 5 degrees of freedom in the joints as a result of the equilibrium between muscle, ligaments, and surface-surface contact. There are also additionally papers available on this method. So to summarize this, with the AnyBody modeling system, you can drive the motion in multiple ways. You can go from having it all measured to having no measurements. The model can be driven by the environment. There is no constraints on the marker protocol. It's very flexible. The intra-joint articulation can be calculated using force-dependent kinematics. So it's a flexible system. There are additional resources. We have a website. There is on this website a publication list. There is a number of webcast and demonstration videos available on YouTube. We also have a forum on the wiki, and inside the modeling system there is a full list of tutorials that covers all aspects of the facilities of the system. Thank you.